Kia ora, Year 12. I hope you're going around at home. We just had a few questions about the textbook questions, so I thought we'd go over that a little bit here. Question 7 to start asks you about where to place the pivot on a rod. Rod looks something like this. The series of dots on it. We've got A through to E. In the middle, we've got C, got B, and D. Okay, these are supposed to be equally spaced. And at A, we have a 5 Newton weight. And then on E, we have a 10 Newton weight. And the question is this, is where does the pivot go? Okay, where does the pivot go to keep it balanced? All right, now the way that we're going to figure this out is either we can just use pure logic to think about it, or we can actually do some maths. All right, so we'll just also label that this distance here is 1 meter. And we can understand that the 10 Newton side will create more torque because it has a greater force, okay? Reminding ourselves that torque equals force times distance, okay? So if we want to balance out more force with slightly less force, we're going to understand that the pivot is probably going to need to be at D, okay? It's probably going to need to be at D. And we can sort of just say that with logic, or we can figure it out with maths if we prefer. All right, now the way that we could figure it out with maths looks something like this, okay? For equilibrium, we have the condition that torque of clockwise equals torque of anti-clockwise. Okay, that would be in balance to be in equilibrium. Okay, now let's say our pivot is somewhere in there. Okay, the rod doesn't have a weight force because it hasn't told us that it does. So we know that the force over here at E is going to take us in the anti-clockwise, and the torque at, sorry, that's clockwise, isn't it? There we go. And the torque at A is going to take us anti-clockwise, if I remembered my rotation. Okay, so what we can do is we can just say perhaps clockwise is torque of E equals torque at A. Okay, now we don't know those torques, so what we can do is expand this out. We can replace torque with force times distance, all right, the other half of the equation. So let's try that, shall we? Force at E, distance of E, equals force at A, distance A. Okay. And what we can do is that if we just replace we replace these forces with the forces given to us. So force at E was 10 distance E equals 5 distance of A. All right, we're getting there. What we can do, try to simplify it down. So we'll divide both sides by 5. Okay, and we should see that this becomes 2DE equals DA. Okay. So, what this tells us is that distance E times 2 equals distance A. Okay, So if we take the distance E and times it by 2, we should get distance A, which tells us that A should be twice as large as distance E, which tells us that this is correct and that the pivot has to go there at D. Okay. And indeed, if we check the answers, we should hopefully be correct. 10B, question 7. Yeah. Now, because it's 2 times that one, we should realize that actually it's not quite on D, because we need to divide this pivot into thirds, because we've got 2 times something equals one other thing. So we want to think about thirds actually, which it makes it a little more tricky. So if we divide it into thirds, we can see that there's a third here, a third, oh no, not quite there. It's hard to draw. There's a third somewhere around here, maybe, and somewhere around here. All right, so it should go roughly here between C and D. Okay, 1/3, 2/3 division. All right, let's move on. Think about question 8, shall we? Scroll on down. Question 8. All right. Parallel forces applied to a light rod. Okay, a light rod means that the rod shouldn't weigh very much or anything at all. Okay, it's trying to get you to ignore that force. All right, so if I just sketch that diagram in here, we have a rod, something like this. At the left-hand side, we have a 5 Newton force up. We have a 8 Newton force down. On the opposite side, we have a 5 Newton force down. And then somewhere in here, we have a 7 Newton, make it slightly longer, there we go, 7 Newtons force up. They've told us that this distance here is 1 meter, and that this distance here is 2 meters. Okay, and they've labelled for us this end is X, this here is Y, and this end out here is Z. Okay, so we've got 3 points. Now, if we want to determine A, the resultant of the 4 forces, what we need to do is start to think about what's going on. All right, forces, it's a bit tricky because if we determine the resultant of the forces, we can cancel them out. All right, so if we go A, we'll go up here, A, resultant forces. Up, how many forces do we have going up? We've got 5 plus 7 equals 12 newtons. And down, we've got 5 plus 8 equals 13 newtons. Okay, which means overall, 1 newton down overall. Okay. Now, because these forces are acting at different distances, it's just something that we have to bear in mind while we try and do this. All right. So, where is that 1 newton down acting? If we think about torque, the total torque for B. Okay, so let's go B. Torque about x. Okay, so that's the question. Talk about x. X now becomes our pivot. So what we're going to do is we're going to redraw it just for x. And the important thing to realize is because at x over here, if we have a pivot, the 5 Newton and the 8 Newton force do not affect it. All right, they can't create a rotation because they're at the pivot. All right, which is our important thing to notice there. All right, so what we want to do is find the total torque about x. So let's label in our forces again. 7 newtons and 5 newtons. Okay, cool. Now, about x. Our 7 Newton force is going to take us up and around this way, okay, which is anti-clockwise. And our 5 Newton force is going to take us down and around this way, which is clockwise. Okay, so we're going to do the same thing as we did before, and we're going to say torque. We're going to try go. If we work out clockwise first, clockwise torque. Sorry, just leaning on the iPad. Equals 5 newtons. Force times distance, it's at distance 3, equals 15 Newton meters clockwise. And then torque, anti-clockwise. Our anti-clockwise one is our 7 Newton force times by distance, which is 2 meters, equals 14 Newton meters anti-clockwise. Okay, so we have 15 going clockwise, 14 going anti-clockwise, therefore resultant of 1 Newton meter clockwise. Okay, which is correct. All right, we can continue to do these same things for parts C. Talk about Y. Okay. Redraw the diagram and we'll understand which torques take us which directions. Okay. So let's get our plank in there. Y is our middle point. Okay, so our pivot is just over here. All right, and because at Y, our 7 Newton force doesn't create a rotation because it's at the pivot, we ignore it. All right, and we just label the other forces. We've got our 5 newtons down. And on our left-hand side, over at X, this is point Z, over at X, we've got 5 newtons up and 8 newtons down, and we know that that should simplify because they're at the same distance to give us, oops, not the eraser, 3 newtons down. Okay, and again, it's really rather simple. Z, our 5 Newton force is going to take us clockwise, and our 3 Newton force is going to take us anti-clockwise. Do the same thing as before. Torque clockwise equals 5 times, and what's our distance there? That should be 1 meter. And the other side, if I was any good at drawing, should be 2 meters. All right, 5 times 1 equals 5 Newton meters. Whoops. And torque anti-clockwise equals 3, because we've cancelled them out, times by 2 equals 6 Newton meters. Therefore, our resultant is 1 Newton meter anti-clockwise. Okay, do you start to see how we're going there? Let's keep going. We'll do the last one. Talk about C. So D, talk about Z. Okay, talk about Z. Draw the diagram again. Planck. We're going about Z, and if we look back at our original diagram, our 5 Newton force acting at Z, we ignore it. So we need our 7 Newtons and our 5 and our 8 again. All right, so our pivot's over here at Z. We've got X over here, we've got Y over here. We know over at X, the resultant is 3 Newtons down, and at Y, we know that there is 7 Newtons going up. It's a bit longer, 7 Newtons going up. Okay, so 3 Newtons is taking us around that way, which is anti-clockwise. 7 Newtons is pulling us up and around that way, which is clockwise. Same process as before. Torque clockwise equals force, which is 7 Newtons. Oops, we don't need the unit there. Times distance of 1 equals 7 Newton meters. Torque anti-clockwise, which is 3 times 3, 9 Newton meters. Therefore, we have 2 Newton meters anti-clockwise, which I hope if we check the answers is also correct. Yep, good. Okay, and the last part here, E, is it in equilibrium? Okay, is the Planck in equilibrium? That's our last question down the bottom here. So let's look back up at our Planck to start with. We want to know, do these forces hold the Planck in equilibrium? Am I right? And the answer should be no, it's not in equilibrium. Okay, what's our reasoning for that? Why is the Planck not in equilibrium? Hopefully, because we can see that the forces are not balanced. Forces are not balanced. Okay, we know that from question part A. We've got 1 Newton down overall. Okay, forces are not balanced, which means F net does not equal 0. Therefore, we are not in equilibrium. Okay, because for equilibrium we need net force equals 0 and we need net torque equals 0. Okay, shall we try number 9? Get some new space down here. 9. A uniform beam 2 meters long is known to weigh between 400 and 500 newtons. Using a spring scale S graduated to 0 to 100 newtons, a pivot block P. An experimental arrangement is made in which the beam balanced horizontally on P and S to enable the weight of the beam to be calculated. Draw the arrangement of the beam S and P that would make this possible. Okay, so what have we got? Well, we have a Planck. We know the Planck is 2 meters. Okay, we know the Planck is 2 meters long. spring scale S. All right, cool. Right, what I think we've got is that we've got a scale that can measure between 0 and 100 newtons. And we've got somewhere to pivot. So what we need to realize is that the weight force of our plank always acts through the center of mass, because we're in year 12 and that's what we do to simplify it. So we know that somewhere here in the middle, we've got our weight force. Okay, and we need this weight force to create a torque on the spring, the scale, so that we can measure the amount of torque that it creates. Okay, so I think what we want to imagine is that if we place the scale down this end, draw it nice and big so I can put an S in it, S for scale, okay, for the plank to create torque on that scale, we need to have the pivot somewhere over here, okay? That way, the torque from the weight force that pulls it in a clockwise direction will create some amount of torque that will require the spring to do some support. Okay, because scales, they actually measure support force and then convert it into mass later on. Okay, so I think this is a good way to be. We want to put the spring, the scale at one end, and we want the torque around the pivot to actually require that support to do something. So the pivot has to be on the opposite side of the weight force, which goes through the middle. All right, so that seems okay. So, in the correct arrangement of the equipment, this is part B. It's 9A. This is part B. The spring scale reads 85 newtons when P, the pivot block, is 0.75 meters from one end. Okay, so they're essentially giving us the diagram with some numbers, which is nice. Okay, so I'm going to redraw it. They're telling us the pivot block here. If we draw like this, it's 0.75 from one end, and the scale is reading 85 newtons. Okay, so the scale is providing 85 newtons of support force up, okay, because that's how scales work. And we're just going to recall for ourselves that the weight force goes through here, FW. Okay, how far is FW from one side? We know it's 2 meters in total. FW is 1 meter, which means the remainder in between the weight force and the pivot, 0.25. Okay, hopefully that's making sense. And the question reads, what are we actually trying to do? Determine the weight force. Okay, weight force is our unknown. Okay, now it says calculate, it's got to be balanced. Okay, so it's saying balanced. And that word balanced means we're in equilibrium. Which means torque clockwise equals torque anti-clockwise. Okay, so let's just realize what's going on here. Around our pivot, the weight force pulls it that way, which is clockwise. Oops. And the support force goes up and around this way, which is anti-clockwise. All right, those are the only two forces we have acting. Weight force of the plank, support force of the scale. Okay, so let's expand this equation out. In the clockwise direction, we have our weight force. So that's FW times the distance of the weight force from the pivot, which is 0.25. And in the anti-clockwise direction, we have our support force, which is 85, times by the distance from that support force from the pivot, which should be 1.25. Okay, if we take 85 times 1.25, we get FW times 0.25 equals 106.25 on that side. All right, and what we're going to do now, divide both sides by 0.25. Cancel, cancel. It's going to give us FW equals 425 newtons, the weight force of the plank. Okay, hopefully that makes a little bit of sense. Whoops. All right, the weight force of the plank down here, that's our final answer. How much does the plank weigh? And we found that simply by knowing that we're in equilibrium, putting in what we know, understanding clockwise and anti-clockwise, and solving for it. Okay, hope that's helping. Let's try do question 10. I only have about 10 minutes until form time, so we'll just try 10, and then we'll come back. I'll do another video for the last two questions. PQ represents a beam, 2 kgs of mass, and at the ends of P and Q, there are supports. A 4 kg mass is placed at 0.5 meters from Q, and the beam is 2 meters long. How much force does the Q exceed the force on P? Okay. Oh, so let's draw a diagram, do this real nice and quick. We've got support at P, we've got support at Q, and we have a mass which is 4 kgs. We know that there's a weight force here, which is 2 kgs, but we've got to turn that into newtons, all right? We've got to turn these into forces. We know it's 2 meters long. And the object is 0.5 from one side. All right, so the question is, how much does the force Q exceed force on P? So we need to find the two support forces. Okay, we'll do P first. To find P, we want to rotate about Q. Okay, we want to do all of our distances relative to Q. All right, so let's find P. Torque clockwise equals torque anti-clockwise. And around when we're rotating around Q, both the mass and the plank take us in what direction? They take us down, they take us anti-clockwise. Okay, and the one going clockwise, we have torque of P is the clockwise one, and in the anti-clockwise, we have torque of weight plus torque of the mass. Okay, so those are our torques. What we've been trying to find, so we've got FP, distance P, equals F weight, distance weight, plus F of the mass, distance of the mass. Okay, FP is the thing that we're trying to find. Okay, this is our unknown, FP. FP is the thing that we don't know. We know its distance though, times by 2 equals the weight force, which is 2 times 9.8, which is 1 meter. plus the mass, which is 4 times 9.8, we convert to weight force, times by 0.5. Okay, I'll just work that out, which is 19.6 19.6. Cool. Fp times by 2 equals, so Fp equals 39.2 divided by 2 equals 19.6 newtons up. Okay, so what we've done is we've found the support force of P, Fp, and what we'll do now is find Fq, and we will compare. All right, nice, as quick as we can. B, finding Q, Fq, we rotate around P. We make P our pivot. Okay, torque clockwise equals torque anti-clockwise. And if we're rotating around P, the things that go clockwise are the weight force, our 2 kg weight mass, and our 4 kg mass, and the thing that goes anti-clockwise is Fq. Okay, so clockwise is air torque due to the weight plus torque due to the mass, and the only anti-clockwise one is torque of Q. Okay, similar process, expand out. Fw dw plus Fm dm equals Fq dq. All right, realizing again that the thing we're trying to find is this one here, Fq. Okay. If we remember from before, our weight force of the plank, 2 times 9.8 times the distance of the weight force from there, which is still 1, plus the weight force of the mass, which is 4 times 9.8 times the distance of the mass from P, which would be 1.5, equals Fq times by 2, because Q is 2 meters from P. Okay, solve those out, and 2 times 9.8, 19.6, plus 4 times 9.8 times by 1.5, 58.8 equals Fq times by 2. So Fq equals 19.6 plus 58.8 divided by 2, 39.2 newtons. Okay. So the question was, how much does Q exceed P? Okay, so Q, Fq is 19.6 newtons larger than Fp. Check the answers, hope I'm not wrong. What are we doing? Oh, yeah, they used 20. I've rounded it. That's a bit cheeky. So that's all good. Okay. I will leave that there. I'll try and return in a minute after form time to do the rest of 10, 11, and 12. All right, kia ora, back after form time. So that was part A. Force Q is about 20 newtons greater than force P. And now what we want to do is part B, which is just asking us what is the anticlockwise torque about P? What is torque anticlockwise about P? Okay, so it wants us to know if P is our pivot, what is the anticlockwise torque around it? So let's just draw our diagram again. P's on the left, so P's our pivot. We've got some forces. We've got our weight force and our mass. Okay, weight force of the plank, Fw, and we've got our mass over here, F of mass as well. Okay, remembering that we have our distances 1 meter and 1.5. So that's 1 meter. This here is 1.5. And we want to know what are those anti-clockwise torques about P. Okay, so what we know is that the system is in equilibrium. Sorry about that, just had to think for a second. Because we know at the end here is our support Q, right? This is support Q, and what Q does is it provides a force F at Q, which provides an anti-clockwise torque. Anti-clockwise torque. Okay, the support provides the vertical force, which provides the anti-clockwise torque to counteract these two torques here, which are both clockwise. Okay, so both these ones go clockwise, and FQ is the only thing that's creating that anti-clockwise torque. So we know balanced torque clockwise equals torque anti-clockwise. So if we can calculate one side, we can know the other side. So let's find the total clockwise torque. In the clockwise direction, we have torque of our weight force plus torque of our mass. Okay, force, weight, distance, weight plus force, mass, distance, mass. Okay, let's go a little further. Our weight force, 2 times 9.8 times 1 plus, was it 4 kgs? Yeah, it was 4 kgs. 4 times 9.8 times 1.5. Okay, and if we multiply that out, 2 times 9.8, 19.6, plus 4 times 0.8 times 1.5, 58.8, which is what we got above, which is good, plus 19.6, and we add those together, we should get 78.4 Newton meters, which is approximately 80, which is what I think they have in the answers. Okay, the rounding's a bit cheeky there. It makes it a bit hard to figure out what's going on. Okay, so that's question 10. You didn't really have to redo this working here. You could have borrowed it from above. We've mostly worked all of that out before. Okay, but just to show us how we do it, we can redo it down there. Okay, if we continue on down, we can do question 11. Okay, we've got a uniform beam in equilibrium suspended by a cord at X. All right, that's fine. Let's draw our beam. Suspended by a cord at X, which from the diagram looks to be just a bit offset from the center. Okay, that's point X. 2 meters from one end, 3 meters from the other. Masses provide forces on each end of the beam of 28 and 10. Okay, so let's simplify that down. On the left-hand side, we have a force like this, 28 newtons, and on this other side, we have a force 10 newtons. Wild not to scale, but it will do. Okay, we also have some distances. This distance is 2 meters. This distance here, again, not very to scale, is 1 meter. Okay. We want to know what is the weight force of the beam, because it's in equilibrium. Okay, so the weight force of the beam weighs some amount and it goes through the center of mass, which is on this side here. Fw is our unknown. Okay, so equilibrium. As always, therefore, torque clockwise equals torque anti-clockwise. We should be pretty used to this by now. In the clockwise direction, we have our weight force, clockwise, and we have our 10 Newton one, okay? We'll call this F1, and this one could be F2, just like to label them. And this one's the only one going anti-clockwise, okay? So let's expand out this equation. In the clockwise direction, we have torque due to the weight force, and we have torque due to force 1. And in the anti-clockwise direction, we have torque due to force 2. Okay, same pattern, expanded out. Force, weight, distance, weight, plus force 1, distance 1 equals force 2, distance 2. Okay, substitute in the numbers we know, leaving out the things we do not know. What we need to think about first is, what's this distance between our weight force in the middle? 0.5 meters, I hope you're all thinking. Okay, the plank is 3 meters long in total, and that means it's 1.5 from either side, and the pivot at X is our, I didn't actually label the pivot, here's our pivot, okay, is 1 meter from either side, so it's 0.5 meters. All right, so let's go like this. Fw times 0.5, because the weight force is 0.5 from the pivot, plus F1, which is 10 times, how long is that side from the pivot? It is 2 meters from the pivot, equals F2, which was 28 newtons, times by distance of force 2 from the pivot, which was 1. Okay, so Fw times 0.5 equals 28 minus 20. Okay, so Fw equals 8 divided by 0.5, so Fw equals 16 newtons. Okay, down. Check the answers very briefly. Hope they didn't lie to you. What have we done? 52 newtons. Oh, I haven't labelled the distances correctly. Damn it. Right. Sorry. I made a clerical error. I hope you spotted it in my labelling up here. Come on, go away. That's not 1 meter and that's not 2 meters. On the left is 2 meters. And on the right is 3 meters. Okay? which means I need to fix all my distances and then hopefully we'll get the right answer. So we'll fix those distances. We'll have to fix those numbers. Oh, this is why we can't do things on video. Okay, so let's try that again. I'll draw it in green so you can see the corrections. The weight force, so the plank is 5 meters long, so it's 2.5 from either side. So actually it's still only 0.5 here from there. So the 10 newtons force is 3 meters from the pivot, and the 28 newton force is 2 meters from the pivot. Okay, 28 times by 2, which is 56 minus 30. Okay, that's still 0.5. 56 minus 30, oops, is 26. Divide by 0.5 should equal 52 newtons down, which is much more accurate. There we go. So, easy mistake to make, getting the distances wrong, but we followed the same method, which is nice. Okay, so that's all that. Let's now think about the last question for the textbook, question 12, and I'm going to have my fingers crossed that I don't make any silly mistakes again. A student balances a 1.5 kg broom on her finger, placing it 1.4 meters from the end of the broom handle. How far from the end of the broom handle will she have to balance the broom if she hung a 400-gram mass from the end of the handle? Okay. So, we have a broom. We can draw it as a plank. Classic physics move. Now, the broom has a weight force. Fw equals 1.5 times 9.8, 14.7 newtons. Okay. And she's going to place a weight force down here, a mass. Okay. And we need to think about how far does her finger have to be. So her finger becomes the pivot. Okay. Now, the pivot in the diagram is drawn as really close to the left-hand side, right? Except in this case, that's no good because both of these forces are going to be clockwise, and it's just going to fall over. Okay, so what we need to do is we need to move the pivot to between our weight force and our mass, the force due to our mass. It's got to be in here somewhere. Okay, so that one will go clockwise and the other will go anti-clockwise, and they'll cancel each other out. Okay, and all we need to do is try and figure out where should it be in there. Okay, so let's go ahead and see if we can figure that out. Okay, so this mass force equals 0.4 times 9.8. We can pre-calculate that to make life easier, 3.92. Okay, now we want to balance it, right? We want to balance it. Balance, therefore, torque clockwise equals torque anti-clockwise. All right, hopefully that's getting familiar to you guys. Clockwise and anti-clockwise. In the clockwise direction, we have our 400-gram mass. Okay. F, M, D, M. And in the anti-clockwise direction, we have the weight force. Fw, distance of the weight force. Okay. Let's put in what we know. 3.92 times dm equals 14.7 dw. All right. we're going to try and simplify it down. So we're going to divide both sides by 3.92. We're going to get down here, dm, just cancel those out so we can see, equals 14.7 divided by 3.92, which was 3.75 dW. Okay, so dm is going to equal 3.35 of the weight force. Now, it's a bit of a funny ratio. What we need to try and figure out is making that a ratio of the how does it have to be from the end, the broom handle. I think this question is crap. I'm actually going to say just ignore question 12. Yeah, don't worry about question 12. We will cross that out. I'll post a little note. It's very hard, and I don't think we need to know anything quite that challenging. Okay, but we do have our ratio of our distances, so you could do something with that. All right, thanks very much. Oops, not the calculator.